everyone, I'm Akshara from Facebook AI Research, and today I will talk to you about sample-efficient learning for legged robots. When we think about learning for locomotion, there are a lot of impressive works that have come out recently. For example, here is a quadrupedal robot which is navigating this really rough, unknown terrain. Here is a bipedal robot which is taught to walk using reinforcement learning. Here is another bipedal robot which is which is running on rough terrain, including with disturbances such as slipping, and a quadrupedal robot which learns to trot, pace, etc. from simulation, and then transfers this to hardware. All of this is really impressive work, which looks fairly different from each other. But if you look closely, they all have one thing in common here. It's that none of them use any visual perception. So especially on the left here, right? So you see this robot navigating this really challenging terrain, but the LiDAR sensor is actually pointing backwards. It's because the robot's not really using this information from the LiDAR sensor to update its navigation policies at all. And this is a really common paradigm in legged locomotion, that they don't take any visual perception. And as a result, they often also don't have any online adaptation. So the top two works here are learned using a simple model or simulation. And then the policy is kept constant on hardware, even though we know that in legged systems, because of contact differences, the behavior between simulation and hardware can be significantly different. There is purposefully no online adaptation in these works. And that's basically what will be the main crux of my presentation today, is how do we teach legged robots to perceive their environments so that they can take into account what's happening around them in making decisions. And then once they can perceive their environments, how do they use this information to adapt their policies? And I will talk about two different unseen settings here. One is transfer to hardware, bridging the sim-to-real gap, and the other is transferring to new legged robots, which were never seen during training. And I want to stress that all of this would be focused on doing this sample efficiently, because legged robots, unfortunately, are also very fragile, and they will break if you take a lot of samples on them. So we want to limit the number of samples we have to take, but adapt our policies online based on environment input for legged systems. So let's first talk about how do we adapt policies online to unseen settings. And in this case, the unseen setting or disturbances come from the sim-to-real gap. So in this work, we basically learn latent representations that are designed for adaptation on hardware for a particular legged robot. And the idea here is that we are proposing a hierarchical control framework, which is learning a low-level policy and a high-level latent action in simulation, which can together basically represent a lot of different behaviors on different legged robots. And then once we have learned this low-level policy and latent representation and simulation, we move to hardware, where we learn a high-level dynamics model, given this latent action space that was learned in simulation. Once both the low-level policy and the high-level dynamics model are learned, we can do model predictive control on hardware to adapt to online disturbances. So how would we learn such a low-level policy and latent representation in simulation? And the main idea here is that our low-level policy pi with parameters theta, along with the high-level latent representation z, should together be able to represent a lot of different walking gaits. So in this case, for all of these videos, we have the same low-level policy parameters theta, but different samples in this learned latent space z, which result in different movements on the robot. So for example, the robot could be turning left, right, going backwards for different paths of this learned latent representation Z. To learn such a latent space Z, as well as the low-level policy theta, we start by collecting expert demonstrations in simulation. So in simulation, we assume we have perfect knowledge of the dynamics of the robot, and we can use inverse kinematics for collecting experts that can perform a large range of behaviors. Next, we randomly initialize a common shared low-level policy theta, but expert-specific latent variables Z. Next, we calculate supervised learning loss with respect to each expert and then sum it together to create the total supervised learning loss over G experts. Now we can minimize this total supervised learning loss to learn one low-level policy parameter theta and G latent variables Z, which basically gives us a setup like this in which multiple experts from simulation are used for learning one common low-level policy and one latent space Z, which can together represent at least the G experts which were used during training. But since now this is a continuous space, Z is actually a continuous space, it can also represent gates that were not seen during training. So for example, by randomly sampling Z and changing Z during this experiment on the right, our robot can go from going backwards using a gallop gate to going forwards using a trotting gate. And by continuously changing Z in this continuously learned space, we can exhibit basically gate transitions on our robots. Now, once we have learned this low-level policy parameterization theta and high-level action space Z, the next thing we do is learn a dynamics model where Z serves as the action. To do this, we basically randomly sample a large number of Zs and measure the resultant change in state of the center of mass of the robot. Given this data, we learn a high-level dynamics model which transitions from the old center of mass dynamic state, a commanded high-level action Z, to the next center of mass dynamic state, keeping the low-level policy pi theta same as what was learned in simulation. Now, once we have learned this dynamics model, F, we can use that for planning over Z using model predictive control to achieve a large range of tasks and optimize many different cost functions. So for example, here is Daisy reaching 8 different goals along a circle using our framework in which the low-level policy was learned in simulation, but the dynamics model was learned on hardware using only 2,000 samples. Now, since this is a dynamics model, it can also generalize to other tasks. For example, trajectory tracking. So on the left is Daisy achieving different trajectories on hardware, and on the right is Daisy following a collision-free path to goal. And in both of these cases, the low-level policy is actually the same, which was learned in simulation. But the high-level dynamics model is different between hardware and simulation. And that's how we can adapt the dynamics model to hardware. We also compare our approach against other learning approaches from literature. And what we observe is that our approach, LAT, is able to outperform other learned hierarchical approaches from literature on velocity tracking, goal reaching, and trajectory tracking, applied to 2 different simulations of Daisy and A1 robots. And the main reason for this is that typically hierarchical approaches from literature are model-free. On the other hand, we are learning a high-level dynamics model, which enables us to generalize to tasks which are very different from what was seen during training. Next, we also compare our approach against inverse kinematics in simulation. Inverse kinematics is a really challenging setting for our approach because inverse kinematics assumes that it has a kinematic model of the robot. On the other hand, our approach does not make any such assumptions about the kinematic knowledge of the system. What we observe surprisingly is that in normal settings, our approach is able to perform comparably to inverse kinematics on both DAISY and A1 simulations, again on velocity tracking, goal reaching, and trajectory tracking. However, because inverse kinematics is making assumptions about the kinematic knowledge of the robot, its performance deteriorates when this kinematic assumption is violated. So for example, in the bottom here, we disable the back two legs of the robot, and inverse kinematics is unable to balance the robot anymore and falls over, while our approach is able to find, still able to find a latent representation Z, which is able to navigate, achieve a lot of these different tasks. And the key insight here was that because we learned our latent representation instead of a hand-designed fixed latent representation for IK, given settings in which the kinematic assumptions are violated, model predictive control is still able to find reasonably good behaviors, while IK suffers significantly more. So, in conclusion, this section of my talk was about how do we adapt policies online to unseen settings. And we proposed an approach here in which we learned latent representations or latent action spaces, which could capture different dynamical properties. And by optimizing in this learned latent action space on hardware, we were able to adapt to unseen settings, including when two of the legs of our robot were actually damaged. Next, let's talk about how can we sample efficiently teach legged robots to perceive their environments as well. So using perception in navigation is fairly common. For example, here is a work which trains a navigation policy in simulation for Locobot and then is able to transfer this on hardware in this particular experiment. But what happens when we take a point nav policy like this, which is trained on a spherical dynamics model, spherical model, so no dynamics, just a sphere moving in space, to a legged robot like DAISY? So the sphere has no knowledge about the dynamics properties of DAISY. So it doesn't know that DAISY has a limited turning radius, it has torque and friction saturations. As a result, DAISY gets stuck on this corner and is not able to reach the goal. So when we want to learn navigation policies on legged robots, we need to take the dynamics of those robots into account. To do this, we again propose a hierarchical control framework where we learn first a high-level policy that reasons about the robot motion using egocentric input of the environment. So it takes RGBD inputs from the environment and commands desired center of mass velocities at 2 Hz. This desired center of mass velocity is taken as input from a low-level policy, which operates using inverse kinematics and a footstep generator to create desired joint angles at 100 Hz for our robots. If we use this kind of a pipeline which incorporates dynamics of the robots into the learning, we can learn hierarchical navigation policies for legged robots. So for example, here is DAISY, which has been trained using the approach I just described, and it's navigating in this new house it has never seen before, and it's able to reach the desired goal. But what happens when we take such a policy, which was trained on one robot, for example, DAISY in simulation, and transfer it to hardware or another legged robot in the same simulation? So here is DAISY, which was trained in this Gibson simulation. It's able to reach this goal. And now we apply the same policy on Aliengo for the same initial and final conditions. And what we see is that Aliengo tends to drift towards the left, and then it exceeds maximum amount of steps and does not reach the goal. So even in the same simulation, for different legged robots, there are significantly different dynamical properties, which will cause a policy learned on one robot to not transfer to another. And we can expect the same behavior on hardware. So how could we learn navigation policies across multiple legged robots? And for this, we propose that we should learn shared navigation policies across multiple robots. And for this, first, we basically propose an off-policy training approach in which we collect navigation data from multiple legged robots, A1, Aliengo, and Daisy during training. Next, the data collected from all three robots is collected into a replay buffer, which then calculates a joint loss used for updating the shared navigation policy. However, each robot's individual replay buffer is also used for updating a robot-specific latent embedding. So while the joint loss across A1, Aliengo, and Daisy is used for updating the shared navigation policy, the robot-specific embedding of Z-A1, Z-AG, and Z-Daisy are updated using individual robot replay buffers. This basically leads to a training approach in which the navigation policy is shared across robots, but at the same time, we also learn robot-specific embeddings. And this has basically several advantages. One, it increases sample efficiency because now you're using off-policy training from data across multiple robots. So we are getting 3 times as much data for the same number of steps per robot, as well as robustness to dynamical differences. So now since A1, Aliengo, and Daisy, all 3 have different dynamical differences, and all of this data is together used for training our shared navigation policy. Our shared navigation policy is automatically robust to these dynamical differences. Now you may ask, what does such a learned robot-specific embedding capture? So what we observe is that once we have learned this robot embedding, and we keep the shared navigation policy fixed, and sample different values in this embedding, we observe different behaviors in our center of mass space. So for example, on the left is Daisy, 4-legged Daisy with Z is equal to 1. In the middle is 4-legged Daisy with Z negative 0.5, and on the right is Z negative 0.7. And these 3 different values of the latent embedding result in very different center of mass behaviors across Daisy. In the left 2 cases, it's not able to avoid obstacles, but on the rightmost case, it's actually able to avoid obstacles and reach its desired goal. Which brings us to basically what we want to do in test settings. So given a new robot, what we can do is search for or optimize for the learned embedding Z, which results in good performance on these unseen robots. So to test this approach, we consider 2 sets of experiments on cart poles, in which we have 3 training cart poles and 2 held out test cart pole models, as well as legged robots, in which again we have 3 trained legged robots, training legged robots, A1, Aliengo, and Daisy, and 2 test held out legged robots, Laikago and 4-legged Daisy. For cart pole, we create these different environments by changing the mass, pole length, and pole offset of these different cart poles. So I would like to draw your attention towards CP4, which is the hardest to control cart pole in our experiments, test cart pole, because it's out of distribution from CP1, CP2, CP3. So essentially, CP5 is testing generalization of our approach for in-distribution systems, while CP4 is testing generalization out of distribution. What we observe is that for training on CP3, learn Z, which is our approach, performs the best, learns the fastest and achieves best performance against a few baselines from literature, as well as against ablations of our own approach. So we compare against meta-RL, Z, which takes dynamics parameters as input, as well as no Z, so learning one shared policy across all card poles, and a fixed Z. So Z is initialized to a random value and then kept fixed. Next, on test systems, what we observe is that on CP4, there is a significant improvement when using our approach, learn Z, versus other approaches from literature, showing that such a learned robot embedding is actually able to generalize to out-of-distribution card poles much better than using other approaches from literature, such as informed Z, which is a baseline which takes the dynamics parameters explicitly as input when learning the latent embedding. Next, once we confirm that our approach works well for card poles, we ran experiments on legged robots. And in this case, we created 3 trained robots in simulation, A1, Aliengo, and Daisy, and then tested our learned policy with new optimized embeddings on 2 previously unseen simulation robots, Laikago and 4-legged Daisy, as well as on A1 hardware. So here is our A1 trained robot. So the robot is trained, but the environment it's put in is a new environment. So it has never seen this environment before. It's able to navigate this environment and reach its desired goal. Similarly, Aliengo, using our shared policy now, can fairly directly reach this desired goal in a new test house. It can turn around and avoid obstacles to reach its goal. Here is Daisy, which is very different dynamics from A1 and Aliengo. Again, trained using our shared policy, is able to reach this desired goal in an unknown house. And here is Laikago, which was a test robot. So we optimized an embedding for this robot in another house, and then tested the robot in a new house, and it's still able to navigate to new goals in this unseen environment. Same for 4-legged Daisy, which is the out-of-distribution robot, which has significantly different dynamics from all of our training robots, and still manages to navigate to a new goal in this test house. Next, we can also transfer the same approach to hardware. So in this case, we do not optimize our embeddings on hardware, but take our shared navigation high-level policy, train in simulation, and apply this to the A1 robot on hardware. And what we see is that despite a lot of sim-to-real differences in the depth camera as well as the low-level policy performance, our high-level policy is learned robustly and is able to generalize to new goals in this completely unknown home that the robot had never seen in simulation. This is also consistent for like a large range of initial and final positions, and the robot is successfully able to avoid obstacles to reach different goal positions in this new house. I wanted to say that here I wanted to say quickly that this was one of the first works that showed that we could train navigation policies in simulation using visual depth input here and transfer them to legged robots on hardware. So I started this talk by talking about how do we sample efficiently teach legged robots to perceive their environments, and I showed some results on one approach which learns hierarchical navigation policies in simulation and then transfers them to new robots as well as hardware. To transfer them to these unseen settings, we adapt our policies online by learning latent representations that essentially capture different dynamical properties. And as a result, In unseen settings, for example, even when two legs of the robot are damaged, we can optimize in this learned latent space to find actions, basically policy representations, which can still achieve a particular task well. Thank you. Here are two papers that I primarily talked about in this talk, and some blooper videos of our robots falling over and running into obstacles when they were supposed to avoid them. Thank you.